Okay, another topic I'd like to review is powers, exponents, logarithms, which I summarized in section 2 of this notebook. Here we go. Here is the definition of integer powers. For any real number x and for any positive integer n, we define x to the nth power as a repeated multiplication like this. X times x times x all the way up to n times. Okay, that's simple. Let's extend this positive integer into 0 as well. So x to the 0 power is defined as 1, but we exclude the special case 0 to the 0 power. So we do not consider that when x is equal to 0. Alright, and then let's consider negative integer power. X to the negative nth power is defined as 1 over x to the nth power, or as a matter of fact, it'll turn out it is equivalent to 1 over x to the nth power if you use the power rule later on. And of course, we don't want the denominator to be 0, so again, we exclude the case x is equal to 0. For this one, it didn't matter, 0 to the 15th power, yeah, that was perfectly okay, but in this case, 0 to the 0th power or 0 to the negative 17th power, those kind of things do not make any sense. Okay, so much for integer powers, and let's go over to rational powers. And we use radicals to prove it. Radicals to establish it, excuse me. Alright, if you have a radical, if you have a rational number, m over n, where n is, the denominator is not 0, and x is positive, then you can define x to the m over n power as nth root of x to the mth power. We have to have positive base, because what if we have negative base? I mean, what do you mean by, say, negative 1 to the 1/2 power, which is square root of negative 1, things like that. See, that kind of thing doesn't make sense. So we do not consider negative base. X has to be positive. And then when x is equal to 0, well, if m is positive, it is okay, but if m happens to be negative integer, then we have denominator 0 situation. That doesn't make much sense either, so we usually consider the case when x is positive. Okay, but there's a bit of a problem of this radical. I mean, we have been using this radical notation for a long time, but is it really well-defined concept? Well, that's something we'll have to come back and prove at some point, and boy, it's not going to be that easy. It is related to that. I mean, for if x is positive, there exists one and only one positive number y such that y to the nth power is equal to x. And that's hidden behind all that. And that unique y will be defined as this quantity. And that's why we can define this nth root of x to the mth power as this y. If there are more than one such y, or if there is no such y, then everything breaks up. And that usually is a big problem. When you define something, you have to be always extra careful about whether it is well defined or not. If it is just plain algebraic expression, okay, you don't have to worry too much about it. But if you have to do any kind of inverse process, always you have to consider that. And that's not always easy. And here's an example. We have something very difficult showing up. And yes, we will come back and prove it. I think we'll have to use the intermediate value theorem, but that's something we'll have to do several weeks later, or maybe in worst case in some other class like Real Analysis 1. At this moment, let's just take it for granted. Yes, let's take this radical expression for granted whenever the base is positive, and define the rational power as radical like this. So whenever we have denominator in the power, it's a radical. Whenever you have negative number in the power, that goes to denominator. We have these four powers, 1, 2, 2, and 1, 2, 3, and 4. And according to those, we have these exponent rules. Now, why do we have these exponent rules? Think about those. I'm going to leave those thinking to yourselves. For example, if you have just repeated multiplication, it's easy to understand this. Repeat multiplying x m times and then another n times, so total m plus n times. And this is division, so x to the nth power, n amount of repeated multiplication of x has we cancelled each other, so we have just x to the n minus n power left. And when n is greater, then we'll have n minus m power left in denominator, so flip it over to numerator, then we have m minus n. And then the 2 is repeated multiplication of m, and that chunk is repeated n times, so their total n times n x multiplied. And then this is just change of order of multiplication. Multiplication and division are commutative, so we have these kind of things. Easy to consider if we have repeated multiplication. In general, a little bit difficult, but in general cases, actually, these will be a part of axiom. Okay, now let's move on to logarithm, the real purpose of this section. Okay, how do we define logarithm? As an inverse process of an exponential, and that is a typical definition in college algebra level or pre-calculus. There's a little bit of problem though. If we have rational power, we can define it using the radical and so on. If you have integer power, yes, through repeated multiplication. Now if y, this power, is irrational, then that kind of thing doesn't make any sense. So what we usually do, we'll have to define the logarithm first and then define exponential as its inverse. In short, later on we're going to define like this. Natural log of x is integral from 0 to x 1 over t dt. We're going to define like this, and we're going to establish all the log rule and then deduce all the exponent rules backward. That's something we're going to do several weeks later, but at this moment let's do it in forward direction, even though there's a big gap where y is irrational. Okay, by the way, here's a visualization of log function and exponential function put together in a graph, and we can manipulate kind of like this. And the default case is when a is e, we have natural exponential and natural logarithm function here, blue and red, and then using this we can change a value, and as you increase a value, the shape of graphs are affected. If I go to the left, and so much that they cross each other, and then pretty soon we are going to have a bifurcation right here, undefined, when a is equal to 1, and then go further and we have completely different shape. So this sudden qualitative change is often called bifurcation. Right here when a equals to 1, and then further than that we have qualitatively different figures. Okay, anyway, we have those kind of pictures. Alright, and then let's go over to the log rules. We have these log rules, everybody knows that, but how do we prove those using the exponent rules over here? Well, that's something we are going to do. Alright, let's do the first one here. We're going to name log a of x as z1 and log a of y as z2. Consequently, we're going to have this expression. z1 is log a of x. Consequently, a to the z1 power is x. By the definition of logarithm, it's inverse of exponential. We just named z2 as log a of y, so a to the z2 power is a y. Again, coming from the definition of logarithm, just inverse of exponential. Now what we do, we want x times y, so we just multiply them together. We have the third line, excuse me. X times y is a to the z1 power times a to the z2 power. Consequently, using the power rule, exponent rule, a to the z1 plus z2 power. Now, express these into the logarithm by the definition. z1 plus z2 is equal to log a of x times y. And what is z1? It was log a of x. What is z2? Log a of y. So substituting, we get what we want. Just a definition, another definition, and then here we use exponent rule. Definition and substitution. That's it. Simple. Let's do this again, this time using division and subtraction. We're going to name z1 as log a of x, z2 as log a of y, and then define, well, logarithm accordingly, and we are going to calculate x over y. Here we go. z1 is log a of x, so a to the z1 power is equal to x, just a definition. z2 is log a of y, so a to the z2 power is equal to y. Great. And this time we divide. X over y is like this, and then we have a to the z1 minus z2 power using the exponent rule. Now, apply the definition of logarithm again. We get z1 minus z2 is equal to logarithm of x over y. And what is z1? What is z2? Substituting everything back in, we get what we want. Precisely the same proof as the previous rule, except we use division and subtraction right here in the third line. See, compare. Everything is the same except here and here. Okay, the third rule, this is going to be a bit easier as a matter of fact, because we have only one logarithm, so we're going to name this one as z. And we use the definition. Log a of x is z, so x is a to the z power. And we want to calculate x to the k power, so let's do that. X to the k power, so it's a to the z power to the k power. This one, so we use exponent rule, a to the kz power. Alright, we have everything. X to the k power is a to the kz power, so if you use the definition of logarithm, we have this. Kz is log a of x to the k power. Kz is log a of x to the k power. And then what is z? Substitute back in, then we have what we want. This is c, so k log a of x is equal to log a of x to the k power, the third log rule. So we can prove all these using the exponent rules. Here are a couple more, but I'm going to leave these to you guys. Change of base formula. And the special case that I'm particularly interested in is this new base is natural exponent e, so that this logarithm is natural log. And same goes here. This logarithm here, base e, is natural logarithm ln. But it works for other positive numbers too. This e can be any positive number here, but I'm particularly interested in the case with the e is Euler number 2.718 something. In any case, I think we successfully reviewed everything about powers, exponents, and logarithms, and we even proved the log rules.